Hello, this is Concrete Path. We have the lecture for the problems for what you call as effective stress and pore water pressure calculations and all that stuff related to that. Let's go for that. Let's go for the problem number 4. We can have problem number 4. We need to get that stress, total stress, pore water pressure, effective stress, those diagrams, distribution diagrams. Okay. Let's see that. What is the soil profile? Let's talk about the soil profile. Soil profile is given. We have sand layer. We have a sand layer. Let's say this is ground level. This is ground level. At 0 meter level, we can write 0 meter level. After that, there is 3 meter level. There is 3 meter level. After that, there is 5 meter level. 5 meter level after that, and after that, final 8 meter level. And water table is somewhere. Water table is somewhere at 3 meter level from the top. So I would say this is your 3 meters. This is your 2 meters. And this is your 3 meters. We can write that also. Total profile is 8 meter profile, soil profile. Sand is there. Void ratio for the sand 0.6. Degree of saturation 0.4. Your specific gravity for the soil solid is 2.65 sand particles. And for the clay, this one is your clay of 3 meters. This is your clay of 3 meters. And for that, your data is given G of 2.7. G of 2.7, water content of 45%, water content of 45%. And this part is all sand. This part is also all sand. Your 5 meters sand, 3 meters clay. Now we need to get those diagrams. Let's go. So this is the case 1 of the problem, part number 1 of the problem. That is the original case. Now from these data we need to calculate the unit weights. Unit weights we need to calculate. I would say the sand above that would be in a bulk condition. That would be in a bulk condition, so there would be bulk unit weight that is equals to G plus SE by 1 plus E. G plus SE by 1 plus E into gamma W. Yeah, we can substitute the gamma W as value of 10 kilonewton per meter cube. So that 10 value of 10 kilonewton per meter cube gamma W. So final value of bulk unit weight 18.06 kilonewton per meter cube. And let's solve for the value of gamma. This would be saturated. Let's solve for the value of gamma sat. This was gamma bulk. Gamma sat for the sand. How much is that? Gamma sat for the sand. So that is G plus SE. G plus SE. Yeah, your value of S is equals to 1. So your S is equals to 1. So G plus E by 1 plus E into gamma W. So that is the equation for that. So that's your 20.31 kilonewton per meter square. Yeah, per meter cube. Per meter cube. After that, we have third one that's also saturated. So we can write gamma sat for the clay. Gamma sat for the clay. That's equals to G plus. See, in this case, your value of E is not given, so we can write G1 plus W by 1 plus E gamma W. So that's 2.75 into 1 plus 0.45 divided by your value of E can be replaced by 1 plus 0.4 G divided by 1. So that's your E equals to WG by S. So into value of 10. So final value of that gamma sat for the clay is equals to how much? 17.67. Now I would say we can use those three values, and all that stuff we can erase now. We can erase all that stuff now. Let's erase this part. We don't need these values now. We only need the final results. We only need the final results. So let's remove all that stuff that was given in the problems. We don't need that. We don't need that now. We don't need that. Okay. Let's write that 20.31. This was your 18.06 gamma bulk. And this was your gamma sat for the clay. That was 17.67. So let's remove this part also now. Let's remove this part. Okay, let's go for the that diagrams for your stress, total stress, pore water pressure, and effective stress. So let's go for the case one, that's total stress. So I would say at the top you are having zero load, above that point zero meters, so zero stress at the top. After that we have gamma bulk into 3 meters, so we have that gamma bulk into 3 meters, so that would be a linear variation of that 3 meter, so 3 meter linear variation, so that's your 18.06 into 3. How much is that? How much is that? 54.18. 54.18 kilonewton per meter square. After that it becomes a surcharge for the soil below that. So after that final, what is the value at this location? What is the increase? This increase would be 20.31 into gamma sat into 2. I would write gamma sat into 2. So final value increase. So final value would be equals to how much? How much is the final value here? So that's 94.8. After that final, there is one more increase. So that increase is that because of 17.67 into 3 meters. So final value at the bottom, total stress at the bottom is equals to how much? 147.61 kilonewton per meter square. Let's go for the pore water pressure. Let's go for the pore water pressure diagram. What is the water table? What is the water table? Water table is up to this point. Water table is from this point. So below that, you would be having hydrostatic pressure distribution for the pore water pressure, positive. So 2 plus 3, so 5 gamma W here, that is 50. And here we have 2 gamma W, that's 20. And above that, that is 0. Is that easy? Let's go for the third one, that's effective stress. That is the difference of the two. Effective stress, sigma bar. Sigma bar is the difference of sigma minus u. So 0 at the top, difference of the two, 0 minus 0. After that, 54.18 minus, at this location, 54.18 minus 0. So that's 54.18. Okay. After that, it would become a surcharge for the soil below. And what is the value here? 94.8 minus 20, that is 74.8. 74.8. And finally, at the bottom, 147.61 minus 50. That's how much? 94 point, yeah, 97.61, is that? 97.61. Final value of effective stress at the bottom. So that's your final, those stress distribution diagrams. I would say that these are your final stress distribution diagrams. Now let's talk about the case 2 of the problem. Case B of the problem is that, case 2 of the problem, case number 2 for that same problem is that water table rises up to ground surface, up to ground surface, or ground level, we can write ground level, GL, ground level. And we need to say find the stress change, find the change in effective stress, find the change in effective stress at 8 meter level, at 8 meter level. So we can directly now calculate only at the 8 meter level. We don't have to draw all those step diagrams. We can directly calculate for the 8 meter level what is the effective stress change at that location. Initially, what was the value? Initially, I would say the change in the effective stress me at the 8 meter level would be initial value of effective stress at the 8 meters. Yeah, final value, it would be final minus initial, final minus uh, final minus initial. It's your initial value at the bottom 8 meter level is 97.61 kilonewton per meter square. Now we need to say what is the effective stress now if water table rises up to the ground level surface. Let's take that case if the water table rises up to the ground level. So your water table is now going to rise up to the water table, up to the ground level. That means water table is somewhere here. So this is your groundwater table now. So groundwater table and ground level overlap now in this case. So let's remove that. So that means your diagrams are going to change. Let's remove all that stuff now. Let's remove all that stuff. Let's remove all that stuff. We only need to calculate at this level, that's at the 8 meter level. We only need to calculate here what is the stress. Let's calculate what is the stress at the 8 meters, total stress at the 8 meters. If the water table is at the top. So what that means? That means this bulk sand is going to change by gamma sat. This is also becoming gamma sat for your sand. Can you say that? Your gamma bulk for the soil that was actually above the water table initially. Now it has become uh, the water table is now above that soil, so this becomes gamma sat here. So the gamma sat for the sand is now here. So gamma bulk is getting replaced by gamma sat. So we can say that your gamma bulk is replaced by gamma sat. So I would say your value of the stress at the 8-meter span would be 8-meter section. This would be in a linear variation somewhat in this fashion. Such that at this location we are having some value of what you call as how much is the sand layer? 5 meters. So I would write this is 5 gamma sat for the sand plus 3 gamma sat for the clay layer. So that's your total stress at the bottom. So 5 into 18, yeah, 20.31. This is your gamma sat for the sand, 20.31 plus 3 into gamma sat for your clay, 17.67. So that's your total stress at the 8 meter level. So that's coming out to be equals to how much? 154.56 kilonewton per meter square. And because water is also there from the start, we would say from the top to the bottom there is a hydrostatic variation of the that pore water pressure, hydrostatic variation, linear variation. So final value at the bottom would be how much? 8 gamma W, that's 80. So your pore water pressure is 80 kilonewton per meter square. So what is the effective stress at that 8 meter level? So that's actually difference of the two. So that's 154.56 minus 80, that is 74.56 kilonewton per meter square. 74.56. 74.56 kilonewton per meter square minus initial value of 97.61. So there is drop. I would say a drop of effective stress. A drop of effective stress is there. A drop of effective stress by how much? Difference of the two. There is 23.25 approximately. This much amount of kilonewton per meter square of the effective stress has got decreased because of water table gets rise into the that ground level. Sorry. Okay. So that's all about that part two. Let's go for the part three of the problem. Okay. Part three of the problem is there. Part three of the problem is there. We need to calculate for the part three. Case number three is there. So case 3 is there. Case number 3, let's try the case number 3. It's saying that find the effective stress at that 8 meter level. But what's happening if water table has been lowered by 2 meters. If the water table has been lowered by 2 meters from the original state, not from the state 2, but from the original state, Originally, where was the water table? This was your water table. Now, from that, I have to lower it by 2 meters. So that means finally your water table finally is reaching somewhere here, 2 meters. If I lower it, so final water table is somewhere here. So that means this part is removed. So for that, let's calculate what is the stress. So I would say, what is the stress? What is the total stress at the 8 meter level? Finally, at this state number 3. Can you tell me? So that would be gamma bulk into 3 plus some gamma is there into 2 meters, some gamma is there into 2 meters, and plus finally your gamma sat for the clay into 3 meters. So all that stuff we know. Let's substitute the values of gamma bulk 18.06 into 3 plus some gamma is there into 2 plus there's some gamma sat, that is we know 17.67 into 3. What about this gamma? What should we write here? If the water table lowers, so there are two options in here. We can have two different options. As the problem does not mention, does not mentions either if this is that what you call as immediate condition, or it's after a long time. So we don't know. We don't know these two conditions, so we can assume any of these. If I try to assume immediate condition, so I can solve. That means if I talk about immediate condition, if I solve for the immediate condition, so I would my solution would be based for immediate condition. I would solve for the immediate condition. Solve for immediate condition. If I try to solve for immediate condition, what's happening? So your water table has been lowered, and at that immediate time, you would say, what is the gamma here? Is that gamma sat now? Is or it would be gamma bulk? So at this, I would say, let's have the water table here. Let's have the water table initially here. At when it is lowers by 2 meters, I would say at the time t equals to 0, when this has happened, at that same time I would say your voids would be still saturated. Your voids will remain still saturated. Why does remain still saturated? Why does remain still saturated? At time t equals to 0, remains still saturated. Similar to that of that excess pore water pressure was there at time t equals to 0. But after a long time, your excess pore water pressure dissipates. Similarly, I would say that those saturated pores would now become dry after a long time. They become in a bulk condition after a long time because all that water would get drained, would get drained. So if I assume that we are calculating for the immediate condition, and gamma would be corresponding to gamma sat. So gamma becomes gamma sat for your that lower part in which water table was lowered. Okay, so that means I would keep the gamma as gamma sat at that immediate condition t equals to 0. At time t equals to 0, just after that lowering of water table, I would substitute the value as the value of gamma sat, and you can keep this in a note, highlighted note. So that's your 20.31. So I'm calculating actually for immediate condition. If I calculate, if it was mentioned for calculate if after a long time, I can substitute here the value of gamma bulk. I can substitute the value of gamma as gamma bulk. At that time, your voids are in bulk condition. That means there would be little bit of water, there would be little bit of air also, gamma in bulk condition. So there would be three state solution. So three-phase diagram would be there, AWS at that time. But in this case, immediate time, I would say I only have two state. I would have only two-phase diagram. Two-phase diagram. That's S and W. So from that, I can calculate now your total stress is equals to. For that calculations, I'm going for your value of how much. You can check that. I think you can check that. Um, so if I solve it for this condition, I can solve it. Let me check that. 18.06 18.06 into 3 plus 20.31 into 2 plus 17.67 into 3. How much is that? 147.147.147.81. And what is the pore water pressure at that 8-meter level? Pore water pressure would be if the level is now here. If the level is here, I would say your pore water pressure would be in this way. Your pore water pressure would be in this way. Your pore water pressure would be here. That's how much? 3 gamma W. 3 gamma W. 3 gamma W. What is the stuff here? What is the stuff we have to keep? So there's a little bit of confusion here. There is a little bit of confusion here. Now if I try to calculate that, if I keep that that water table is somewhere here, but if I assume that voids are still saturated, if the voids are still saturated, that means there would be water also. There would be water also in that case. In that case, there would be water also. So there would be different values. Let's say my value of that effective stress would be a difference of the two. Difference of the two. That's 147.81 minus 30. So that's 117.81 kilonewton per meter square. So this is your value at the 8-meter level. Now, if I try to calculate for what you call as, if I try to now calculate for after a long time, let's calculate for that after a long time. stresses at that 8-meter level. Initially, I would solve for the total stress. So I would write that equation, same equation we had to write now again for that condition. So at that time, I would say your voids in that part where you have lowered that water level, in that part your soil would be now in bulk condition. So for after a long time, your soil would be now in a bulk condition, bulk state. So this would be also gamma bulk. This would be also gamma bulk, and initially top one was also in gamma bulk. So I would write here gamma bulk into 2. So this would be 18.06 into 2. So final value would be here. That's 147.81 minus, I would subtract that 20.31. So from this value of 18.06. So that value final 143.31. So this is the value. And what I would say, what is the gamma W here? That is 3 meters, 3 gamma W. So pore water pressure would remain same, 3 gamma W. So final value, difference of the two for a long time, your effective stress would be difference of the two, that's minus 30, that's 113.3 kilonewton per meter square. So I would prefer that second one. I would prefer second one. That water table is lowered and we are calculating after a long time. So try to prefer second one. That second one is there. Now let's go for the part D of this case number 4 of this of this same kind of problem. Same kind of problem is there, and part number 4 is there. Case number 4. Case number 4 is there. Number 4. Case number 4. Calculate the effective stress at the 8-meter level if water table rise 1 meter above ground level. 1 meter above ground level. Let's have that. That means remove this part, remove this part, remove this level, remove this all that level, remove all that stuff, remove all that stuff, remove all that stuff. Water table has been risen to 1 meter above ground level. If this is your ground level, water table is now somewhere above that. Water table is now somewhere here. So this is your water table. So this is all because of water. So I would say this is your 1 meter because of water. So this is water, and this is your 1 meter. And in that part there is no soil. No soil is there. Okay. Let's try to calculate the effective stress. Effective stress. Let's try the equation for effective that total stress first. First we would calculate total stress. Sigma at 8. Sigma at 8, that's actually 1 gamma W. 1 gamma W plus this one, as the water has been as we have what you call as risen the uh, water table to the 1 meter above the ground level, so all those soils would be saturated. All that soil is saturated now, so we had to solve for the gamma sat. So gamma sat we had to take. Gamma sat is actually how much? Gamma sat was your 20.31. So I would write 20.31 gamma sat into how much meters we have? 5 meters of that sand layer plus uh, after that gamma sat for the clay, that was how much? 17.67 into that 3 meters of that clay layer. So that final value of sigma at 8 is equals to 164.56 kilonewton per meter square. Now let's calculate the value of pore water pressure at that 8-meter level. So I would say your variation would be, because we have water at this level, so it would be a hydrostatic variation, and at this level we are having 9 gamma W. That's actually 1 plus 8 gamma W. 1 meter because of the water only, and this is in the soil, saturated soil, so 1 plus 8 gamma W. So that's actually 90. So difference of the two is actually 164.56 minus 90. How much is that? 974.56. So you would compare this value with the case that was original, with the case number 2. You compare this value with the case B, with the case B. What was in that case number B? Your case number B was somewhat in this fashion, that groundwater, that your water table is coinciding with groundwater table. Ground level is equal to groundwater table. So this was your level of the water table. So at this location, then we said that what was the effective stress at that time. This was also same as that of this case. Once, that is 74.56. You can check that value also. So from that we can have conclusion that by increasing the water above that ground level, there is no effect in the change. There is no change in the effective stress. No change in effective stress. No change in effective stress by increasing water above groundwater, above ground level. I would write above ground level. Let's say at the, if the water table was about if this is your ground level and groundwater table was also there, so we are having some stress at this location. Let's say this is your sigma bar equals to 100 megapascal, or we can write kilonewton per meter square. And if I increase now water table above that, let's say our soil now becomes in this fashion, that this is our soil, this is your soil. Now we are adding water for some height of h above that water, above that ground level. This is your ground level, and your water table is somewhere here. This is your water only of height h. Your effective stress would not change. Total stress would change, but your pore water pressure is also changing. So that means your sigma equals to u plus sigma bar. Your sigma is increasing, but your pore water pressure is also increasing, but sigma is remaining constant. Sigma bar is remaining constant. So we can write here sigma would remain is equals to 100 kilonewton per meter square. Because the increase of sigma results in increase of u, such that your sigma bar is not increasing, does not change. Delta is equals to 0. Change in sigma bar is equals to 0. So that's very important conclusion also. So I would say let's pause that. Let's pause that. Let's pause that. Okay, that was a beautiful problem we have. Let's take two more. Let's take two more problems. Let's take problem number 5. Number 5. Compute that what you call as total stress, effective stress, pore water pressure at 12-meter depth. At 12-meter depth, below the bottom of the lake, below the bottom of lake, below the bottom of lake. Your lake is actually how much? Deep, 6-meter deep lake is there, and below that there is soil, and at the soil 12-meter depth from the bottom of the lake, we have to calculate that those stresses. Let's go for that. Let's say that there is some top surface of that lake, and it's how much deep? 6 meters. So this is your deep 6-meter deep lake. After that we have clay, and clay layer is greater than 15 meters. So clay layer is greater than 15 meters. Clay layer is greater than 15 meters. Let's say that this is your clay layer extension, but we'd have to calculate only up to the level of 12 meters. 12 meter. So 12 meter is somewhere here. Let's say this is your 12-meter level. So I would say this is 12-meter clay. Clay is there. This is your clay. So at this location, we need to solve for, let's say this is point B. We need to calculate those stresses at this point B. So this is only water. This is water, and this is soil. This is water. So we are having that water for 6 meters and clay for 12 meters. So I would say clay would be saturated. So for that, gamma would be saturated. And let's see the data given to you for the clay. Water content of 40%, specific gravity 2.65. So from that we can calculate gamma sat. Gamma sat would be G 1 plus W, 1 plus W divided by 1 plus WG, 1 plus WG into 9.81 into 9.81. So that is your gamma sat equals to 17.66 kilonewton per meter square per meter cube. 17.66. Let's erase all that stuff. Let's erase what do you call as let's erase all that stuff. We are only getting this gamma sat equals to 17.66 kilonewton per meter cube. So I would calculate total stress at this location. So at this location, I would say what is the total stress at that location, at that point P? That is actually how much? How much is that lake? 6 meters, and this is your 12 meters. I would write your total weight above that section. Total weight above that section. That's because of water. Gamma W into 6 meters plus your gamma sat of the clay. Gamma sat into 12 meters. So that is 9.81 into 6 plus gamma sat of how much is that? 17, 17 point, 17.66, 17.66 into 12. So that's your total stress at that point B. How much is that? How much is that? 270.78 kilonewton per meter square. And let's calculate the pore water pressure at that location, point B. So pore water pressure variation would be a linear variation, hydrostatic variation, because water table is here. So it would be a linear variation. Linear variation, that's 18, we can write 6 plus 12. We can write 6 plus 12 into gamma W. So that's how much? 176.58. So finally your effective stress at that location, 12 meters from bottom of the lake, is equals to difference of the two. How much is that? That's 94.2 kilonewton per meter square. 94.2 kilonewton per meter square. We can directly also calculate it in this way, that this is also equals to, I would write, if I try to directly calculate that, I would say your there is no effect of this part. For the calculations of the effective stress, there is no role of the water above the soil, because effective stress talks about soil. If there is no soil, there is no role of water for your effective stress. Talks about soil only. No role of water. If there is no soil in this part, I can ignore this part. I would only solve for this part. I would write your gamma for this for 12 meters. Here we can write gamma sat. I would write effective stress at that location 12 meters would be actually equals to your gamma sat for the clay into 12 meters minus gamma W into 12 meters. That's actually gamma submerged into 12. We can also calculate gamma submerged, that is G minus 1 by 1 plus E into gamma W. If you try to multiply with that 12, so you'd get the same value of 94.2 also in that way. Okay, let's go for problem 6. I think that's the final one. That is the final one. Final one, that's final one for your effective stress, total stress, pore water pressure. Number 6. So we have that soil profile. Is there. Groundwater table, ground level is there. There is 1.5 meters. Gamma dry can be calculated by N, that is porosity of the soil. Specific gravity 2.7, 1.5 meter layer. Then 1.8 meter layer is also there. Gamma bulk can be calculated by, because we have water content of 15%. After that we have one more soil, that's gamma sat. That's because we have water table here. Water table is there, so that layer is 4.7 meters. So the total depth up to this level is 8 meters. So this is your 8 meter level. 8 meter level is there. This is 8 meter level from the top. Okay. Now what's happening? What we need to calculate? Get set go. Get sigma bar 8 meters below the ground level. So we need to calculate effective stress at this location. Effective stress. Okay. So based on the data, can we calculate those values of gamma and dry? So that's actually G plus. Yeah. First we need to calculate. We need the calculations of void ratio from the porosity. We have the equation n by 1 minus n. N by 1 minus n. So get the value of porosity. We get the value of void ratio 0.54, and from that we can get the value of dry density G gamma W. G gamma W by 1 plus E. How much is that? 17.2. 17.2. After that, gamma bulk. Gamma bulk can be calculated as gamma dry into 1 plus water content. Can we? I think we can do that. Also 1.15. So how much is that? It's 19.78. After that, gamma sat. Gamma sat is actually G plus E. G plus SE. I would write G plus E. G plus E divided by 1 plus E. G plus E by 1 plus E. Your value of E we know. Your E is actually 0.54. Your E is actually 0.54. G plus E by 1 plus E into gamma W. So that value is how much? How much is that? That value is 20.64. 20.64. So let's remove all that stuff now. So we know that how to calculate gamma. So we already know that. So let's use only those values. Let's remove all that stuff. I would write we are having gamma dry of 17.2, gamma bulk of 19.78, gamma sat of 20.64, and we need to calculate what is the total stress at this location. 8 meter. Can we calculate total stress at this location? sigma equals to 17.2 into 1.5 plus 19.78 into 1.8 plus 20.64 into 4.7. That's actually gamma dry into height h1. So we can write that as actually gamma dry gamma dry plus into h1 plus gamma bulk into h2 plus gamma sat into h3. So after that we can say what is the pore water pressure. So for the pore water pressure to be calculated, I would say it would remain zero for the soil for the soil above the groundwater table, and after that it is a linear variation as that of a hydrostatic pressure. So final value at this location would be 4.7 gamma W. 4.7 into 9.81. How much is that? 46.107 kilonewton per meter square. And finally, your effective stress at that 8-meter location would be your total stress was how much? How much was that total stress? 158.412. So 158.412 minus 46.107. How much is that? That's your solution for the answer for the problem. That's how much is that? 112.3 kilonewton per meter square. So let's go for the part 2 of the problem. Part 2 of the problem is there. Part 2, case number 2, I will write. Case number 2 of this problem is there. So calculate the change in effective stress if the water table suddenly drops the water table suddenly drops to a level of 6 meters below the ground level, to a level of 6 meters below the ground level, 6 meters to the below the ground level. So initially it was at what location? It was at 3.3 meters. 3.3 meters. Now it's falling to the location of 6 meters below the ground level. 6 meters somewhere here. 6 meters. So such that final value this becomes 2 meters and groundwater table is somewhere here. Can we say that? So, and if it talks about suddenly, we can say that if it talks about suddenly, I would say we can talk about immediate condition. I would be solving for immediate condition. If it talks about suddenly, I can solve for the immediate condition. Okay. Now, I would say because so for the immediate condition, I can have those values of gamma. I can have those values of gamma. Let's try to have those values of gamma. So now our water level is here. Water table is here. Groundwater table is here. So the level, the soil below that would be in the saturated condition. Gamma sat 20.64. Gamma sat 20.64. And the soil already that was initially the water table was here. So soil above that is in dry. After that, soil is in bulk, and this was actually in the gamma sat. Now, as I would say, because for the immediate condition, I would say the soil pores would still remain saturated. Soil pores remain still saturated. Remains still saturated for the immediate condition. Remains still saturated. Can we say that? So we can have the gamma of gamma sat for that part where there is lowering. So in this part we can say that we can use the concept of gamma sat. We can have the gamma of gamma sat. I can solve for the value of gamma sat. I would say I can use the value of gamma sat. Now there's one more possibility if you solve for the long time also. So I can also solve for the long time also. Let's solve for the value of gamma sat. That's immediate condition. So I would write what is the effective stress. That is actually 17.2. I would write gamma bulk into 1.5 plus gamma bulk. Yeah, this was your gamma dry initial one. Initial one is gamma dry. After that we have gamma bulk into 1.8. Gamma bulk into 1.8. After that we have gamma sat into, how much is that difference? What is the difference here? This is actually 6 minus 3.3. That's 2.7. So this part is critical here. Plus after that we have gamma sat into 2 meters, because this part is 2 meters now. So what is the total value gamma? What is the total sigma? 158.4120. 158.21 158.4120. 1.5 gamma dry, 1.8 gamma bulk, 2.7 gamma sat, 2 gamma sat also. Okay. So that is the solution. So we can have final answer of that gamma, that is total stress, that is 158.4120 kilonewton per meter square. What about the pore water pressure? So pore water pressure, I would say pore water pressure would be only for this part, that is 2 gamma W. So that's 19 point some value, 19.62. So your effective stress final value is equals to 158.4120 minus 19.62. So this is the difference of the two, that is 138.7920. I have calculated it for the immediate condition. Now if I try to calculate for the second part, that's if I try to calculate for the second part, that's if I calculate for after a long time, after a long time, after a long time. So for that, I would say your lower part of this 6 minus 3.3, this would be now in bulk condition. This would become now bulk condition, gamma bulk, as per the soil above that, gamma bulk. So I would say this part becomes gamma bulk. So in this case, I would write here your stress becomes gamma sat. In terms of gamma sat, I can replace gamma bulk. If it's mentions, so you had two options here. Either you can solve for one of the part, or you can solve for both of the conditions. You can solve for immediate condition, you can solve for long time, or if it is mentions directly that calculate for either of the conditions, so you can have that concept. So but for better understanding, you can solve for both of the conditions. Okay, so gamma bulk is there, and there is 2.7. So all other stuff is same, all other stuff is same, except that your gamma bulk is going to here your gamma is going to change. Initially it was gamma sat, now it becomes gamma bulk. So final value would become different. You can calculate that. That would be lesser because gamma bulk is lesser than gamma sat. So this would be lesser. This would be lesser, and your pore water pressure would remain as it is 2 gamma W. So final value of sigma would be lesser as compared to the initial case, as compared to the immediate condition, as per the calculation we have. And third part of the problem is there, we need to calculate. Third part of the problem, case number 3, calculate the shear strength. Calculate the shear strength for the sand. This was actually sand. All that soil profile was actually sand. This was your sand. 8 meter layer of sand was this. This was all about sand. Calculate the shear strength of sand for both the conditions. For the case number 1 and case number 2. Calculate the shear strength. I would say we haven't touched this topic. So shear strength is actually equals to sigma tan phi, and this is actually sigma dash. That is the effective stress. Effective stress sigma tan phi plus c, and it is given that that internal friction phi. Your value of phi for the sand is 30 degrees, and we can substitute those. And I would say if the sand is cohesionless, c is equals to 0, so we can substitute the value. So for the initial case, s1 equals to sigma 1 tan phi, and for the second case, S2 equals to sigma 2 tan phi. So what is the value of sigma in the second case? Effective stress, that is 132.792. So we write that for the second case into tan of 30, tan of 30. And in the initial case, we had that sigma dash. What was this value of sigma dash in the initial case? That we have also calculated first in the case number 1. That was some value of 94.2. 94.2. Is that? Yeah, that was 112. That was 112.3005 kilonewton into tan 30. So you can solve that. So your strength 1, strength 2 is equals to, in the initial case and final case, 64.8 and 78.8 kilonewton per meter square. So that was all about that problems. So thank you for watching. Thank you for watching. Thank you.